so, you've seen this work as an electromagnet, right? But when you actually look at it, it's not a very strong electromagnet. So I have this steel ball here, which I can attempt to pick up using this electromagnet. And I will, put through maximum current like I did before, after this cools down a little bit. The thing is with the wires heating up, it's a vicious cycle. The more it heats up, the resistance increases. So anyways. So now let me turn on the magnetic field to the maximum possible. And when I try to pick this up, I can't really pick it up. But you have seen me actually pick up the steel ball before, right? How did I do that then? Like if this magnet is right now strong enough. Now, you might not remember how I did it. Do you know, have you seen electromagnets, that like practical electromagnets people use? Is it really literally just a coil of wire, or are there other parts to a practical electromagnet?
Other parts.
Okay, what are the other parts?
Flat, another flat piece of ferromagnetic piece on it.
Well, if it has a ferromagnet, then it's not an electromagnet.
Or like another, another piece of like iron.
There's another piece of iron. It's the iron core. So this is I think it's a ferromagnetic. I don't know exactly what it is, but it does stick to magnets, so I think it's at least the ferromagnetic. So I have a ferromagnetic material, and when I put it in here, and so right now it doesn't work because this is not an actual magnet. It's just a piece of iron or something close to it. But once I turn on the current, now the magnetic field will be strong enough to actually pick this up. So let's try that. So turn it on. Yeah, now it's strong enough to pick it up fairly easily. In fact, I can go down in current quite a bit before it drops the ball. Okay. Yeah, I only needed something like 1 ampere of current, a third of the current that I was using to pick up this ball. So what happened? Why is the magnetic field now stronger? Like I still have the same amount of current. I didn't really change the current. So this is the reason I had to cover dielectric when we did the electricity. Because the concept that's involved here, it's easier to introduce once you have seen the dielectric. So let me draw the modified solenoid magnet. So this is the modified solenoid magnet that you have seen. Modified solenoid electromagnet. Then I have, let me draw it this way, the side view. So I still have the loops of current. Let me just draw this way in the side view. Okay, that's probably enough. So let me finish drawing the current. So I have current going into the board here. Currents coming out of the board here. So this is a cutaway view of the solenoid. What I drew on my left with a perspective view. What I drew here with the perspective view, I'm just showing you the cutaway side view. You have to sort of imagine the circular looping here. So the way I've changed it is I put a piece of iron here. So this, instead of being an empty space, instead of being vacuum, now it's a piece of iron here. There's some material here, just call it iron. And somehow this iron being present here made the magnetic field strength greater. Magnetic field strength in particular, I guess inside iron, who knows what it is, but when you look at the magnetic field at the bottom, that's where you can see with that stainless steel ball that magnetic field here is greater in strength. Yeah. So at this point, what I want to remind you of for the comparison purposes is the dielectric that we briefly mentioned when we did the electrostatics. So for comparison, recall dielectric. In what context did we talk about dielectric? Do people remember? There was a particular electrical device where, I mean, you know, when you say dielectric, the word simply means insulator. Like anything that's not a conductor is a dielectric. So, yeah, with the capacitors, that's where the dielectric played an important role. In fact, I still have yet to demonstrate this 1 farad capacitor, but like you couldn't build this 1 farad capacitor with an air gap or a vacuum gap. It's just impractically large. So to make this, they have to use dielectric. So that shows up in the capacitor. So, so this is the model of a capacitor. Remember the parallel plate. You have 2 conducting plates here, and 2 conducting plates that's hooked up to a battery, for example. Then, you know, hooked up to the battery, then one is at higher voltage than the other. So there's an electric field. There's an accumulation of charge on these conducting plates. And the role that the dielectric played was it allowed you to store greater amount of charge on these 2 plates while applying the same amount of battery voltage. So the way we modeled it was, all right, so if I have some insulating material here, so if I have some dielectric here, then this gets polarized. Let me just draw one row of polarized molecules. So this gets polarized with the negative charge getting attracted to the positive, and the positive end getting attracted to the negative end. And the effect of this polarization was that you had an accumulation of negative charge on the surface of dielectric here. That couldn't actually combine with this because it's an insulator. Those charges are not free to leave the dielectric. So you had an accumulation of negative charge here, and you had the accumulation of positive charge here. And what these charges do is they cancel out the electric field from these free positive and negative charges. So that, so you know, if the electric field inside the material is weaker, then the voltage that you need to apply to maintain this is lower. Or put it the other way, you can apply a higher voltage. Sorry, with the same amount of voltage, you can now store higher number of charges here because the electric field, due to much of this charge, will get canceled out by these charges, surface charges that develop on the dielectric. So the electric field inside here will be what it was before. So the line integral of electric field will give you voltage, the same voltage as before. But the amount of charge you ended up being able to store on the capacitor increased quite a bit with the use of dielectric. All of that beginning to come back, like what dielectric is? Yes? So here's the question. How would we model dielectric? So, this is changing the way some of our devices behave. So there must be some numerical parameter that we can use to model the behavior of this dielectric. How did we model this? I mean, there must be some number that experimentalists can measure, right? I mean, if you are looking at it really at the fundamental level, property of dielectric, it relates to polarizability. Like when you apply electric field, how easily does it polarize? But we are not going to get into that. But I want to point out a particular physical constant that we used, or I said that we would use to model the dielectric, because that'll help you make sense of the physical constant that we are going to use here to model the things like this iron, model the magnetic material. So anyways, if you're talking about electricity and constant, what are some of the constants that's important? Do you remember the names of any of those constants? No one remembers anything about electricity? Yeah, epsilon is the how we wrote it down, right? It occurs in particular in Gauss's law. You know, Gauss's law is written as the electric flux is equal to amount of charge enclosed divided by epsilon naught. So the old-fashioned term for this constant here is what's called permittivity. Permittivity of free space, meaning vacuum. So this is Gauss's law in vacuum. So when you have some material like dielectric, what that does is what the eventual effect of this is this modifies Gauss's law. So instead of having permittivity of free space in vacuum, you could have permittivity of whatever this dielectric is. So to apply Gauss's law to this situation, you would replace this constant with just epsilon, and that would be the permittivity of the dielectric that you are using. Or you could call it dielectric constant. At some point, you have to be careful with who's using which term in what way. But the key thing here is that this dielectric modifies the form of Gauss, this constant that we are using in Gauss's law. So instead of it being some universal constant that applies to vacuum anywhere, it becomes a constant that characterizes property of material. So Miguel, any idea what else might change in this Gauss's law?
The distance from
Gauss's law, it has nothing to do with the distance here. There's no expression for distance in Gauss's law, right? So what else changes in Gauss's law? This is not something you actually, we went over in class. But so here's the reason I'm pointing this out. So if you still apply the original Gauss's law, if you apply the original Gauss's law of this form, E dot dA is equal to Q enclosed over epsilon naught, this is a fundamental law of nature. When you define some Gaussian surface here and apply it here, it should still work. So when I say modify the Gauss's law, it's more of coming up with a model that's useful in a lot of situations, but not always. But the original Gauss's law is still the fundamental law. So we changed one part of it, what used to be permittivity of free space. We changed that to dielectric constant of whatever material is here. And there has to be one more thing that changes along with it, so that what I write down here is essentially a version of the original Gauss's law. And this gets into the topics that would be more appropriate for upper division level. So let me just write it down and we'll move on from that. So here, what we would say is, so when I'm modifying it this way, instead of charge being the total enclosed charge, it would be the total free enclosed charge. As in, when I use this version of Gauss's law, sometimes we call this Gauss's law in matter. Because here's the thing about these charges that charges that show up as a result of this polarization, you have no direct control over that. The only thing you can control are the free charges, the charges that are free to move around, charges that you place there. So when you use this Gauss's law of this form, then the charges that you are counting, you don't count any of these positive charges. The only charges you would count are these negative charges here, the free charges that are on the conductor. Okay? So when you are using the original version of Gauss's law, then you count both the free and the bound charges. Okay? But does all of this kind of make intuitive sense? Yes, yeah. So the reason I want you to go over that is, because this is easier to describe in electricity, and all of this makes some intuitive sense. We are not going to get into detailed calculation of any of this, upper division level, I'm not going to do that. But at least the scheme of how we do this makes sense. Yeah?
If there's not a dielectric in the middle, where are the bound charges?
Then there are no bound charges.
Oh, okay.
Yeah. So in vacuum, then both of these take the same form, where the epsilon, the permittivity would be permittivity of vacuum. Yeah. It's only when there's matter here, insulator there that can get polarized, then you draw the distinction between bound charge and free charge. And in this form, you don't count, with the permittivity of the material, you only count the free charges. In the original Gauss's law, you count all the charges, whether it's bound or free. Yeah. So, but, once again, the actual full treatment of this will take too much time, but that's the scheme that we have in electricity. What I'm going to tell you is that we sort of transfer it over here for magnetism. So you have the fundamental law for magnetism, Ampere's law. So when you look at the Ampere's law, the line integral of B dot dl, it's a line integral, not a magnetic flux calculation, that's equal to mu naught times current enclosed. And this mu naught is what's called permeability of free space. So once again, the old-fashioned term for this constant, a lot of people call it magnetic constant these days, but this is called permeability of free space. And this is the constant that we are going to modify whenever we are dealing with magnetism in matter. So iron, it's a ferromagnetic material, right? So we are going to assign a permeability mu for iron. So when you look at this permeability of iron, what you find out experimentally is that this is much greater than permeability of free space. Then I want you to look at the effect of having this here. So when you look at the magnetic field, so when you look at the magnetic field here, imagine this Amperian loop that we are working with the last time. So the amount of current that's enclosed didn't change. And this is where it gets a little bit murky. There's no such thing as a bound current. So that's why I did this first. Here I'm just I'm still counting only this current, and free current is all the current there is. There's no bound current. There's such a thing as magnetic polarizability, but I'm not gonna go in there. When you look at Ampere's law, then if you have higher value of this permeability constant, so if it's in matter, now this simply becomes mu, not mu naught. It'll be permeability of whatever material you have, whatever material. So the amount of current that's going through the coil, it's determined by the power supply. It's not changing. So this permeability constant is getting bigger. Then what you find is that the magnetic field must be bigger so that this relationship is still true. So the magnetic field in this region is greater than without the iron. And if the magnetic field inside the iron is greater, then the magnetic field outside also has to be greater. It cannot suddenly go from strong magnetic field to weak magnetic field suddenly. So that will be the modification of this constant will be the reason we use certain materials when we build particular devices so that they become practical. One example you are seeing right now is the electromagnet. When I'm building an electromagnet, I'm going to put a iron core inside it so that it increases the magnetic, the permeability constant and makes the magnetic field stronger. Sometimes it's strong enough that it'll hold up. No, sorry, this is too heavy. Never mind. It's not quite. I mean, if it's at an angle, sometimes it can hold itself. Yeah, but I think if it's completely vertical, then it'll fall out eventually. Anyways, so that's one. The another device that you will see later in one of the inductor lab is this. This is not just a green-looking random ceramic. This is called the ferrite core, and the reason for this ferrite core is to provide this high permeability. It's a high permeability material that will make the magnetic field inside stronger, given the same amount of current, which will increase what's called the inductance of this toroid material that you will see, I guess, on Wednesday. Okay. So, for the purpose of this lower division class, this is as far as we are going to get. That when you have some material inside the coil, then instead of using the permeability of free space, mu naught, we'll replace it with the permeability of the magnetic permeability of the material. And while we are on magnetic permeability, I should mention this one last thing, which is kind of contrast between magnetism and electricity. So when you are dealing with electricity, you have seen the special roles that conductors play, right? So this is a piece of aluminum, so it's still a conductor, which means if you apply voltage at one point, the entire aluminum piece is at the same voltage once it's at electrostatic equilibrium, right? Yes? Those conductors which are special, so actually conductors can be modeled as a material that has infinite permittivity. So, conductors can be polarized so well that it would, So you don't actually do it that way. When you do it properly, it actually has like imaginary permittivity. But one of the naive ways you can handle it is you can treat it like an insulator that can be polarized easily well. So conductors are special in static electricity. In magnetism, it's not. Like, any regular conductor, it doesn't get picked up. In fact, in magnetism, the conductors are so unspecial that they don't even really shield magnetic field. Like, watch. The magnetic field, it's at a distance, but it just goes through this conductor and affects these two magnets as if this conductor isn't there. So, that's So the kind of material that would have a big impact on magnetic fields are limited. It's not as, conductors are like everywhere. It's very common. But the kind of magnetically special material, they are limited. Essentially, you have ferromagnetic material, that's one. And you have two more types of material which have a relatively large magnetic effect, which I'll give you the names so that in case it comes up later in your field of study or whatever, you can say you have heard of it. One is a superconductor. Yes? I mean, everyone here have some sense of what superconductors are? And superconductors have a particular effect called Meissner effect. And I guess the best recommendation I can give you is find the Meissner effect video and watch it. You can. Oh. I don't. Never mind. It's too small. So this is kind of what you would see: magnet levitating above a superconductor, because the property of superconductor sets up persistent current within it that does interesting things. So superconductor is one magnetically special material, but it's special in a whole bunch of different ways. If you are working specifically with the magnetic fields, one specially designed material that has a special magnetic property, but it's not a ferromagnetic thing. It's not a superconductor. Is I guess it can go by two different names. You could call it high permeability metal. I don't know if that's a common term. High permeability metal, or yeah, this is the more common term, mu metal. So if you know people who work with NMR or anything dealing with magnetic fields, then stuff that's made out of this type of mu metal is common. So it's not nickel iron. That doesn't sound right. So I don't think mu metal is actually ferromagnetic, but it has a high. Mu metal can actually shield magnetic field, whereas if you built something similar with this piece of aluminum, it wouldn't do anything to the magnetic field. So I think that's everything about magnetism in matter that I want you to mention. For the purpose of this class, really the only thing that matters is that a material can have magnetic property. We characterize it with the permeability. And in most of the problems where you need to know that, like a solenoid with an iron core or an inductor that's wound around the ferrite core, somebody will just give you what the value of the constant is. And you just use it instead of permeability of free space.